Hello, I'm Matteo Hessel, and I'll be teaching the reinforcement learning module together with Hado and Diana, and today I'll be talking about models and planning. In the past few lectures, we already covered quite a bit of material. So we started with the bandits, this minimal instantiation of the RL problem, where we are allowed to disregard the sequential nature of decision-making and focus exclusively on trading off exploiting existing knowledge versus exploring alternative courses of actions that might seem suboptimal now, but that might turn out to be even better as we gain experience in the environment and the world around us. We then discussed dynamic programming and model-free algorithms as two families of ideas and approaches that allow us to solve both prediction and control problems with and without access to a complete specification of the environment. Finally, we introduced function approximation as the leading approach to scaling up these families of ideas to settings where we might have very large state spaces or even continuous state spaces. If we look back at dynamic programming and model-free algorithms, we can roughly sketch the underlying principles and differences between the two in the following way. So in dynamic programming, we assume we're given access, a privileged access, to a complete exact specification of the environment dynamics. That includes both the state transition and the reward dynamics. We then just need to solve for this perfect model, and we don't need to interact with the real environment at all. In model-free algorithms instead, we do not rely on any given form of model. Instead, we learn values and policies directly from interaction with the environment. In between these two extremes, there is a third prototypical family of algorithms, which is typically referred to as model-based reinforcement learning. Here we are not given a perfect model, but we do attempt to learn at least an approximate model, but while interacting with the environment. And then we use this learned model to derive values and policies. A visual depiction of the model-free algorithm would be seen as implementing this loop, where we act according to our current value estimates and our policies to generate experience. But then we use this experience to directly update our values and our policies. And instead, the model-based algorithm would add a step of indirection in this loop, whereby we act according to our current value estimates and policies, just like in model-free RL, but we use the resulting experience to learn a model of the state transition and the reward dynamics. Then we can use the learned model instead of the experience directly to update the values and policies, thereby closing still the loop. And of course, boundaries between these two families of algorithms don't need to be extremely rigid, and we can perfectly imagine to combine the two ideas and use experience to both update values and to learn a model. We can still then use the model to perform additional updates and to refine our value estimates. And today we will actually discuss a popular instantiation of this idea, which is the Dyna algorithm. But whenever we delve into a new topic, I think it's always good to stop a second and reflect on the motivations that underlie a family of ideas. For instance, there is obvious disadvantages to this line of attack. If we first learn a model, then we use the model to plan a value function, there are two sources of errors. Because whatever model we learn from data is likely not to be perfect. It will incorporate certain approximations or certain errors. And these will compound with additional errors that arise when planning with the model to estimate values. In contrast, if you consider model-free algorithms, they use real data that is always correct to update the values, and therefore there is only one source of approximation, which is the value estimation process itself. Despite this, though, there are reasons to believe that model-based reinforcement learning could be quite effective. The first of these reasons is that models can be learned with supervised learning methods, which are very well understood and very powerful and effective. Additionally, explicitly representing models can give us access to additional capabilities. We could use them to represent uncertainty or to drive exploration. And finally, but not less importantly, in many real-world settings, generating data by interacting with the environment is either expensive or slow, or both of these. And instead, computation is getting cheaper and cheaper by the year. Therefore, using a model to perform additional updates could allow us to trade off compute for a reduction in the number of interactions that we need with the environment. And this will make our algorithms more data efficient and therefore extend the range of problems we can successfully apply them to. We will start now with a bit of due diligence in a sense. So we'll start by discussing different types of learned models and how to train them. And only then we will delve into concrete algorithms for planning. But before we go there, if you need a moment before jumping in, this is a good spot for a break. If we're going to learn a model and use a model for planning, the first thing to discuss is what constitutes a model in the first place. And in this course, a model will be an approximate representation of an MDP. And for now, we will assume that the dynamics of the environment of this MDP will be approximated by a parametric function with some parameters theta, and that states and actions in the model are the same as in the real MDP. And also we will assume that given states and actions, sampling from the model will estimate the immediate successor states and the immediate rewards that we would get by executing those same actions and those same states in the real environment. And it's good to realize that this is not the most general characterization of a model. There are other types of models we could consider that are quite related to this, but different. And we will actually discuss a few of these in following lectures. So for instance, we will consider and discuss non-parametric models, where we use the data directly to sample transitions in the environment. And also backward models, that models, for instance, the dynamics of an inverse MDP, rather than the MDP you're directly interested in. And also jumpy models, where the actions do not directly map on the set of primitive actions in the MDP. We will discuss some of these later, but for now let's focus on the simplest kind of model, because this is already sufficient to discuss quite a big range of ideas and support a good range of planning algorithms. So with these premises, the problem of learning a model from experience basically can be formulated as a supervised learning problem, where our dataset contains a set of state action pairs, and the labels of these are the true states that we and rewards that we will observe when executing those actions in those states. And the parameters of the model will then have to be chosen, as in standard supervised learning, so as to minimize some prediction error on this data. Defining a procedure for learning a model will then amount to picking a suitable parametric function for the transition and reward functions, picking a suitable loss to minimize, and choosing a procedure for optimizing the parameter zeta so as to minimize this loss. So for instance, we could choose to parameterize transitions and rewards using some linear mapping from a suitable encoding of states and actions onto, for instance, the rewards and some encoding of the successor state. And then minimizing the parameters could be achieved by using least squared. This would give us an expectation model, for instance. And specifically will give us a linear expectation model. Note that this is not the only kind of expectation model we could consider. So for instance, using the same kind of loss, the same mean squared error, we could, for instance, parameterize the model itself, both the reward and the transitions, using a deep neural network, and maybe use gradient descent instead of least squares to optimize the parameters. Regardless of the specific choice of the parameterization, though, it's good to understand what are the pros and cons of expectation models in general. So some disadvantages, for instance, are quite obvious. Suppose you have some macro action that randomly puts you either to the left or to the right of some wall. Well, an expectation model would, for instance, put you inside of the wall, which might not be a physically meaningful thing to predict in the first place. Interestingly, though, the values could still be correct. So if the values specifically are a linear function of the state or of the encoding of the state, then actually the linear transformation will commute with expectation. And therefore, the value of the expected value of the next state will actually be the same as the value of the expected next state, even though the expected next state might have some peculiar features like placing you in the middle of the wall. And this actually applies regardless as to the parameterization of the model itself. So it only requires the values to be a function, a linear function of their state representation. But additionally, if both the value and the model are linear, then this even applies to unrolling the model multiple steps into the future, which is quite a powerful and interesting property. It might still be that we're not willing to accept this trade-off. So we might it might not be possible to make either the value or the model linear. And in this case, maybe expected states might not be the right choice, because the values that we can estimate from expected states might not have the right semantics. We might not be able to derive expected values from expected states. And in this case, we could consider a different type of model. So we could consider what is called a stochastic or generative model. So generative model generates not expectations, like an expectation model, but samples. So it takes as input a state, an action, and a noise variable, and it will return you a sample of a possible next state and a possible reward. And if we can effectively train a generative model, then we can plan in our imagination. So we could, for instance, generate long sequences of hypothetical transitions in the environment and compare them to choose how to best proceed. And this could be done even if both the model and the values are not linear. The flip side, of course, is that generative models add noise via the sampling process. There's also a third option, which is to actually attempt to model the complete transition dynamics. So model the full transition distribution and full reward distribution. And if we could do so, actually, both expectation and generative models and even values themselves could be all derived as a subproduct of our model, of our full transition and reward model. The problem is that it might be hard to model the complete distribution, or it might be computationally intractable to actually apply it in practice due to the branching factor. So for instance, if we were to try to estimate the value of the next state with a one-step look ahead, this would still require to sum over all actions, and for each action sum over all possible successor states. And things get exponentially worse if we even want to look multiple steps ahead. And as a result, even if we had this full distribution model, some form of sampling would probably be needed for most problem of interest. And in that case, the advantage of the complete distributions compared to, for instance, just a generative model might be smaller. In addition to the type of model we might want to train, there is the second additional important dimension, which is how we parameterize the model itself. So a very common choice is to, first of all, decompose the dynamics of the reward and the transitions into two separate parametric functions. And then for each of these, we can choose among many different parameterizations. In this course, for instance, we'll consider table lookup models or linear expectation models, and finally also deep neural network models. In the table lookup case, the model is an explicit representation of an NDP, where, for instance, we may estimate the probability of observing a given successor state for a given state action pair as the empirical probability based on past experience. And similarly, we could parameterize the reward function as the empirical mean of the rewards that we did actually observe in practice when executing a given action in a given state. In this case, we would actually get a mixed model, because our table lookup model would use a full distribution for the transition dynamics and an expectation model for the rewards. It is, of course, possible also to model the complete distributions for the rewards themselves. So let's consider, for instance, our minimal reinforcement learning example, where we have the usual two-state MDP with no discounting, and we observe 8 episodes of experience. So once in one of the episodes, we start in A, we transition to B, and we observe no reward. In all the other episodes, we start in B, and we terminate immediately. And in all but one, we observe a reward of 1, and in one of them, we observe a reward of 0. A table lookup model would model the complete distribution of the environment dynamics as in the picture on the slide. So in state A, with probability 1, we transition to B, and we observe the reward of 0. And in state B, with probability 1, we terminated, but with probability 0.75, we observed the reward of 1, while with probability 0.25, we observed no reward at all. If instead we consider a linear expectation model, it's good to remember that first of all, we need some feature representation to be given to us, because a linear model doesn't have the capability to build its own state representation. But given this some feature representation, we could encode any state S as some feature set, for instance, a vector, and then parameterize separately reward and transitions as 2 linear functions of the features of the state. So for instance, expected next state could be parameterized by a square matrix, TA, 1 for each action A, in such a way that the matrix times the features of the current state give us the expected next state. And similarly, rewards could be parameterized by a vector, WA, for each action A, so that the dot product between the vector and the current state representation gives us, again, the expected reward. If we do so, then on each transition where we execute some action A in some state S, then observe some reward R in next state S prime, there we can apply a gradient descent step, for instance, to update both WA and TA so as to minimize the mean squared error on both the reward and the expected state. We are now ready to delve into the true heart of this topic, which is how to actually use models to plan. And specifically in this section is how to do so for the purpose of improving our value function estimates and our policies. So the core, let's say, value proposition of planning and in general of model-based RL is the capability of improving such value estimates and these policies by absorbing compute, but without requiring actual interactions with the environment. As you might remember, dynamic programming is actually a good example that we have already seen of a process that allows to do just this. The problem is, of course, that in dynamic programming, we're given privileged access to a perfect specification of the environment, but in reinforcement learning in general, we're actually interested in planning algorithms that do not make this assumption, and instead perform planning, for instance, with the learned models, such as any of the ones that we discussed in the previous section. In this case, the simplest approach to get around this limitation of dynamic programming is maybe to just directly mirror dynamic programming algorithms, but plugging in a learned model in place of the privileged specification of the environment. If we do so, then we can just solve for the approximate MDP with whatever dynamic programming algorithm you like. So you could use value iteration or policy iteration. And by doing so, we still require some interactions with the environment because we will still need to learn the model. But at least, hopefully, we can reduce quite a bit our reliance on real interactions and therefore be more data efficient. So this approach actually can work, and it's a reasonable thing to consider. But it's also not the only option. So for instance, there's another route we could take. So we could combine learned models not with dynamic programming, but instead with the ideas and algorithms that we discussed in the context of model-free agents. So this is also referred to as sample-based planning. And very simply, it works by using the learned model to sample imagined transitions, so imagined trajectories, and then applying your favorite model-free algorithms to the imagined data, just as if it was real data. So for instance, you could apply Monte-Carlo control to SARSA or Q-learning, and just apply the same updates on the imagined data as sampled from the approximate NDP that you have learned, as if it was real data sampled from the environment. And let's consider a concrete example to make this clearer. So this is the same example that we discussed in the previous section. So on the left, we have the real experience we have access to. So 8 episodes, most of them starting in a state B, and then observing either a 0 or 1 reward, and one actually starting in state A and the first transitioning to B. And in the middle is actually the learned table lookup model that we had learned from such data. So this gives us a 100% likelihood of transitioning from A to B, and a 100% likelihood of terminating in B, but with a 75% probability of getting a reward of 1 and 25% of getting a reward of 0. The idea of sample-based planning would be take this model and then sample trajectories, episodes from this model. And this could be, for instance, the data that we report on the right. So all of this data is sampled from the model that we have learned. And for instance, we have now 2 episodes that start in A, both of which transition to B because this is forced by the model. And then in this case, both episodes were sampled a reward of 1 when they were in B, plus a number of episodes starting in B and terminating immediately, again, consistently with the model. So what happens if we apply Monte-Carlo learning to this data? Well, we will get, for instance, that the value of A is 1, because in both episodes, when we start in A, we collected a reward of 1 at the end. And a value of B that is equal to 0.75, because in the sampled episodes that we got from our model, 3/4 of the time we observed a reward of 1 in B. So in this case, it's perfectly in line with the learned probabilities from the model. So this is a cool idea, and also using dynamic programming directly with a learned model could be a very interesting approach. But what are the potential limitations with both of these ideas? As always, the the greatest concern is that the learned model might not be perfect. So actually, in general, we know it will incorporate some errors and some approximations. And in this case, the planning process may compute a policy that is optimal for the approximate MDP, but that is suboptimal with respect to the real environment. And so our presentation couldn't be complete if we didn't discuss how to deal with these limitations. And there are many ways we could go for this. So one approach would be very, very simply, whenever the model is not good enough, is not reliable enough, just use model-free algorithms. Another idea would be, let's try to reason explicitly about our uncertainty over our estimates of the model. So for instance, this would lead us more towards the Bayesian approach. And finally, the third approach, which is what we will delve more in today, is actually to combine model-free and model-based methods, integrating learning and planning in a single algorithm. How can we do this? Well, in the previous discussions, somewhat implicitly, we already discussed that there are two potential sources of data, two potential sources of experience. So one is real experience. This is data, transitions, trajectories that you generate by actually interacting with the environment. And another source is simulated experience, where the data is sampled from a model, for instance, a learned model, and therefore is sampled from some approximate MDP. Well, the core idea behind Dyna, which is a powerful approach to integrate learning and planning, is let's just treat the two sources of experience as if they were the same thing. So while in model-free, we learn values from real experience, and in sample-based planning, we plan values from simulated experience. Well, in Dyna, let's do both. So let's apply the same update to values and policy, regardless of whether data comes from real or simulated experience. And this very directly implements the picture I had also shown at the very beginning of the chapter. So where I suggested we could maybe act according to our value estimates or policies to generate experience. And then this experience could be used both to update the values and policies directly, but also used to learn a model that could then generate additional simulated updates, simulated experience. So let's now discuss concrete instantiation of Dyna, because this idea is very general, but of course we could plug many different algorithms to this and apply very different updates to both the simulated and real experience. So what does this actually mean in practice? Well, a popular version of this idea is what is typically be referred to as Dyna-Q, where we use Q-learning on both the real and simulated experience. And this is what it looks like. First, we, of course, need to initialize now both value function, like in Q-learning, but also a model, because we will be training it alongside. And then on each step, we can select actions using an epsilon greedy policy, for instance, like in standard Q-learning. And after executing this action, we, of course, get from the environment a successor state and a reward. With this real transition, we can directly apply Q-learning, for instance, by updating the current Q values towards the usual target constructed by summing the reward and the discounted max Q value in the next step. But we can also update now the model in a supervised fashion. For instance, in a tabular deterministic environment, this would just amount to storing the next state and the reward. The next point is where the secret sauce, in some sense, of Dyna comes in. So basically, for each real step in the environment, we now perform n planning updates, where we take some past state action pair that we have encountered during training, and we use the current model to sample a possible next state and a possible subsequent reward. And we use this imagined transition to perform an additional Q-learning update. And of course, as we increase the number of imagined steps that we do, we can basically reduce our reliance on the real transitions and become more data efficient, as we were hoping. Interestingly, of course, there are many different ways of extending or implementing this idea. So for instance, we could use a different model-free algorithm instead of Q-learning. Also, the algorithm right in the slide is written for the tabular setting, but of course we could use linear functions or deep neural networks to represent both the values or the models. And alternatively, we could also vary the amount of planning that we do over time. So very intuitively, the model typically is improved and updated along the way, so it's hopefully getting better over time. So maybe we could imagine to perform more planning updates as training progresses and we become more confident in our model. Ideally, we would actually even have some form of uncertainty estimates that we can use to choose how much planning to perform and how much to trust our planning updates, depending on the accuracy of our learned models. But regardless of the details and potential enhancement, the important thing is that even this basic algorithm already instantiates the most fundamental properties that we were looking for. So we can sink in more compute to learn more efficiently, which I just want to recall again, it's really critical if the data is slow or expensive or unsafe to collect. And this, I can't say this enough, it's really often the case in many real-world applications. So let's take a look at what happens when we actually run these algorithms on a simple problem, just to gain more understanding and intuition about planning for credit assignment. To do so, we will consider a simple maze, which is drawn on this slide at the top right, where on each episode, the agent starts on the cell marked with an S. And from any cell, the agent can take one of 4 actions, which correspond to moving up, down, left, and right, respectively. The dark cells instead are walls, meaning that if we try to move into one of these darker cells, the action will have no effect. We'll just bang on the wall and stay where we are. The reward is 0 everywhere, except for a single positive reward that you collect when you reach the goal cell, which is the one marked with a G in the top right corner. Under this setting, it's fairly obvious that the optimal policy for any discount smaller than 1 is going to be a policy that leads you from S to G following the shortest path, because any choice of actions that will take you along the longer path will basically result in the final reward be discounted more strongly. And this means that we can evaluate the quality of the policy learned by an agent, for instance, by plotting the number of steps that the agent takes in order to reach the goal, as a function, for instance, of the number of episodes that it has experienced. And this is what is shown in this plot on this slide. This plot is taken from the Sutton and Barta book, so you can also read there about more details about how exactly this was instantiated and run. But fundamentally, this plot just shows 3 instantiations of the algorithm that I showed in the previous slide that were ran with different amounts of planning. Specifically, it was ran with 0 steps of planning, meaning that the algorithms just revert to vanilla Q-learning, or with 5 steps of planning, or with 50 steps of planning. And what is really apparent already from this plot is that vanilla Q-learning takes many tens of episodes to actually converge to the optimal solution. And instead, by just adding a tiny bit of planning, so just doing 5 additional updates for every real update, the agent manages to converge to the optimum much quicker, in less than 10 episodes. And as we increase, for instance, to 50 planning steps, the agent actually converges in just a couple of episodes to the optimal policy, which is really impressive. It might even seem too good to be true in a sense, like what is actually happening behind the scenes. And in this slide, I'm trying to give you basically an opportunity to peek behind the scenes and see what happens to the Q-values estimates as we run this algorithm. And specifically, let's consider what happens on the very last step of the first episode. So this is when it's basically the first time the agent observes the reward. So for simplicity, we will also assume that Q-values were initialized as 0 everywhere. Under this assumption, without planning, the first episode is actually fairly boring. So on all intermediate steps, the values were 0 when the agent enters the cell, and actually stay at 0, because the TD error is always 0. Our estimates are 0, the rewards are 0, the max Q value we bootstrap on is also 0. So no update is done throughout all the first episodes. Only a single Q value is updated right on the last transition. And this is the Q values corresponding to moving upwards from the cell immediately below the goal, immediately below that top right corner cell. And when the agent is doing this final transition of the first episode, that Q value is correctly updated towards the goal reward. And this immediately makes a greedy policy optimal in that one cell, because all the other action values stay at 0, but this action value of moving up from the state just below the goal becomes actually has a non-zero value. So all other states that we have seen throughout the first episode have not been updated. Q values stay all at 0, and therefore the behaviors stay random, assuming we are breaking ties at random. But this very last state, that is shown in the bottom left of in the maze shown on the bottom left, well, that one gets updated to the correct policy. On the maze shown on the bottom right, we show instead the state our estimates of the Q values when we run the same algorithm with 50 steps of planning. And again, we freeze the algorithm immediately after we have run it for just one episode. But suddenly you can see that the Q values have been updated throughout the maze. So it's not just the final state that has realized what the optimal action is, but actually the model, the estimate of the Q values that the agent has updated throughout this first episode show a meaningful direction for many, many different other states. And basically the information of how to move from the state to the goal has propagated almost all the way to the start, which is quite impressive. And the reason is that when you do update that first, that last cell in the episode, you then start sampling 50 more updates on imagined transitions from the model, which means that on each of these other 50 planning updates, we will be able to propagate information from the new updated Q values backwards in state space. And this means that, well, in this case, it doesn't quite solve the problem in a single episode, but it will just take just a couple more episodes to correctly propagate all information through the state space and figure out what the optimal policy is. Of course, this is not all roses, right? There are always certain critical issues with model-based RL, including the fact that in some cases our model will be wrong. And in this experiment, I'm trying to give you some intuition of how wrong models can affect learning in a model-based RL system. So to gain some intuition of this, let's use again the same algorithm to investigate how an incorrect model may affect training. And we will do so by simulating this model being wrong by having a sudden change in the dynamics of the problem. This means that the model learned from the agent in the first half of training will suddenly be wrong because the world itself has changed. But the effect of this on learning will be quite different depending on the type of error. Let's see what I mean by this. Well, in the first setting, we assume that at the beginning of training, the environment looks like on the grid on the left, where there is a short path between the state, marked with S as usual, and the goal, marked as G in the top right corner. And once the Dyna-Q agent has learned this policy correctly, which is shown in the plot by the cumulative reward becoming linear in the number of steps, well, at that point, we change the environment to the one on the right, which is very similar grid. But now, the optimal policy is not anymore to move to the right to reach the goal, but rather the agent needs to take a detour to circumnavigate that wall that is now blocking the path. When you do this change in environment, suddenly the cumulative reward collected by Dyna-Q flattens, because at the beginning, the agent will try to continue move through the same path that it had learned at the beginning, but of course that path is now blocked because the walls have shifted. And this means that for a few steps, the agent will be unable to collect any rewards. But if you look at the plot for Dyna-Q, after a while, the agent does start collecting more rewards because the agent will update the model to now correctly understand that it cannot move through that cell because it's now a wall. And through planning, it will then reroute the policy of the agent by updating the Q values in order to take a different route, and which now results in the reward again growing linearly with the number of steps. There are several specific agents on this plot, and again, this plot is taken from the Sutton and Barton book, but that correspond to slightly different instantiations of Dyna. And the middle one is Dyna-Q, which is the canonical one I described, while Dyna-Q Plus adds some small exploration bonus, which means that it actually is able to reroute slightly faster. But the core message remains that if the model is inaccurate in this way, where the world actually is harder than the model was initially assuming, the behavior of the agent is such that it will actually lead to real transitions that will correct for the model error. And therefore, in some sense, the learning dynamic is overall quite benign. But it's good to realize that this is not always the case. So let's now consider a very similar setting with a slight difference. So now again, the world changes, but the change in environment is actually easier in some sense. So at the beginning, you have the situation on the left where the agent needs to take this detour around the wall in order to reach the goal. But after changing, there is now the detour is still available to the agent, but another path has opened up. So the agent could pass to the right of the wall, which is a slightly shorter path, which would result in a higher reward. What happens is that once Dyna-Q agent has learned to correctly take this detour, long detour around the wall in order to reach the goal, there is nothing that pushes the agent to explore this other path. The way in which the model is incorrect, the fact that there is actually a shorter path, is not reflected in the data that the agent sees, because the error in the model doesn't result in data that can correct for the model error itself. So what happens is that once the agent has converged on this solution of taking the long detour, it actually might just stick with this behavior, and it will take a very, very long time in order to realize that there was actually an error. And this is why in this plot, the Dyna-Q algorithms, which is exactly the one I described in the pseudocode before, will actually continue learning at the same speed. The slope is the same because it's still taking always the same long path in order to reach the goal, after that the world itself has become easier. And here you can see actually the Dyna-Q plus that adds this exploration bonus is actually able to figure out this additional path. And I don't want to go into much details about Dyna-Q plus because the details are not important here. But the important thing to understand is that thinking deeply, for instance, about exploration is still important, even in model-based RL, because the certain types of errors in your model might not necessarily be discovered unless you have something that pushes your agent to execute this behavior that results in useful data. The Dyna algorithms I described in the previous section is a beautiful instantiation of a system that integrates learning and planning, so model-free and model-based updates, but it's not the only one. And in this section I want to discuss experience replay and its connection to more conventional model-based algorithms such as Dyna. Traditionally, RL algorithms did not explicitly store experience, so it was trivial to place them in one of two groups. So model-free methods that do not attempt to explicitly model the dynamics of the environment and directly update values and policy online with the latest data. And model-based methods that learn transitions and reward model and then plan value functions using such a model. But this kind of sharp distinction is blurred not just by algorithms like Dyna that do both, but by other developments, for instance in the space of model-free algorithms. And indeed, many modern RL systems now store transitions in an experience replay buffer, and then apply model-free algorithms not just to the latest transitions, but also to past transitions in the buffer. And this is actually a fairly common technique for model-free agents, but it also can be seen as just instantiating Dyna, but with an experience replay playing the role of a non-parametric model. And this is not just a superficial similarity, because both systems actually share a fundamental property, which is the ability to sync in compute, as I said many times, with no additional environment interactions to improve values and policies. And in this case, the experience replay systems would do so by making many updates on past experience for every new real steps in the environment. In this plot here, I can show that how this property of the scalability property of planning algorithms is instantiated by both Dyna and a replay Q-learning agent in the case of a simple grid world. So this is a simple grid world where, as usual, you start in the state S and you need to reach the goal G as fast as possible because there is some discount strictly smaller than 1. And what I show on the right side is basically the total number of steps required to reach the goal on the top right 25 times, every time you start from the cell S on the left, as a function of the amount of planning, so of the amount of updates that you do for each real step in the environment. And you can see that regardless as whether the entire transition is replayed, like in an experience replay system, or whether a model is used to infer the subsequent rewards and state given a state action pair, the profile actually looks very similar. The more additional updates you do for every real step in the environment, the more the performance improves, and so the faster you reach the goal, which is basically the lower the total number of steps that are required to reach the goal 25 times. And you might be even tempted to take this to the extreme. So are experience replay system and algorithms based on learned parametric models completely equivalent? And well, in a tabular settings, we can actually derive exact equivalences between certain model-based and model-free algorithms. And even more in general, somewhat trivially, if we had a perfect model that outputs exactly the same true reward and successor state as the non-parametric replay system, well, the two would be exactly equivalent by construction. In general, though, of course, any model that we use will not be perfect. So one question that you may ask is, will it ever be better? Could the inaccuracy that almost certainly come from using a parametric model provide benefits on top of a non-parametric replay system? This seems unlikely, and I think it's fair to say that if we only use the model to reconstruct the rewards and successor states corresponding to an observed state-action pair, it seems hard for a parametric model to improve over just replaying those transitions. But the reason that algorithms like Dyna and model-based RL that use parametric learned models are so important is that actually a parametric model allows flexibility that goes way beyond that. So for instance, we could use the model to plan for action selection. And this is something we'll discuss in great detail in the next section. Because if you can query a parametric model for actions that you could want to take in the future, then you can use this to construct a plan to decide how to act. And this is something that you cannot do if you just have a non-parametric replay system that can only tell you which action you took in the past in a given state. Additionally, with a parametric model, you could do things like counterfactual planning. So query models for actions that you could have taken in the past, but did not. And related to counterfactual planning, you could do what is called backward planning. So if instead of modeling the actual dynamics of the problem, you model the inverse dynamics. So given a state and an action, the model tries to predict what was the previous reward and previous state, well, then you can use this to assign credit to states that could have led to a certain outcome, in addition to assigning credit, as in standard RL, to the states that actually preceded that outcome. And finally, if you have a parametric model, you could train this model at different timescales. Like an algorithm like Dyna needs not to be restricted to train a model exactly on one-step transitions. And on the true native timescale of the environment, you could train a model to do jumpy predictions and therefore support what is called jumpy planning. And in conclusion, it's actually worth noting also that there are computational differences between the parametric model and experience replay. And this might also actually play an important role in choosing between the two. So, for instance, querying a replay buffer is very cheap. Given a state-action pair, it gives you immediately what was the reward and what was the successor state that you observed in the past. While given a state-action pair, generating a subsequent reward and state using a learned model could be very expensive if the learned model, for instance, is parameterized by a big neural network. And if you look at memory, of course, things change. And for instance, the memory requirements of a replay buffer can be quite harsh because the memory will scale linearly with its capacity, while a parametric model could achieve good accuracy with a fixed and comparably smaller memory footprint. And overall, I think the key takeaway that I would like you to get is that both are important and powerful ideas that implement this core principle of planning, this capability of syncing in compute in order to improve our learning and our algorithms. And regardless of the labels that we want to attach to them, it's really more important to just think deeply about the problem that you want to solve and whether a parametric or a non-parametric model can be the best fit for that specific problem. So far we discussed how planning can be used to improve our estimates of a global value function or a global policy that is applicable in all the states of our MDP. But now I want to tell you about a different form of planning where we sync in compute as usual without requiring additional interactions with the environment, but for the purpose of just selecting a single action in a single state. This is something that is also called planning in the now. And it may seem a special case of the previous problem, and of course in a sense it is, because if we could get perfect values and perfect policies everywhere, then we could just use these perfect values in any one state. But the motivation for investigating planning for action selection is that sometimes it's actually easier to make a very accurate local value function than it is to actually fit a global value function. And the reason is that in planning a value function for the current state, we only need to take into account the distribution of states that are reachable from the current state. And that might be a very small portion of the overall MDP. And additionally, planning for action selection has a few other appealing properties, like the fact that suppose you have some inaccuracy in your model in some states. Well, that will only affect the local throwaway values that you're using to select an action right now, but it won't pollute like a shared global value function that is going to be reused everywhere. So it might result in, sure, selecting a suboptimal action in certain poorly understood states, but maybe that just leads to reasonable exploration and, for instance, behaviors that can help you correct the model itself. The simplest form of planning for the purpose of action selection is what is called forward search. So this approach allows you to select the best action in any given state by basically building the entire search tree that has the current state as root and then follows all possible trajectories from the current state onwards until episode terminations. Basically, this approach amounts to representing as a tree the entire sub-MDP of reachable states from the current one. And in some cases, this sub-MDP might actually be fairly tiny, and then you can maybe solve it in full every time you need to select an action. In general, of course, this might not be the case. So in general, the number of the states in the tree will actually grow exponentially, for instance, with the depth. And so even with a fairly small action space, it might be computationally intractable if the horizon that you need to look to goes beyond a handful of steps. But this is still a reasonable thing to consider, at least from a conceptual perspective, because then, sure, we have a problem with branching, but we have dealt with branching in the past. So similarly to how we did for learning global value functions, we can again use sampling also for solving these local MDPs just for the purpose of action selection. And this actually results in what is called simulation-based search. Here, we construct a partial tree. So basically, we start as usual from the current state as the root of some tree, but then we construct a subset of the full tree by simulating multiple episodes of experience that all start from the current state and then use the model to roll forward possible sequences of actions. If you construct such a partial tree, then you can just, for instance, apply model 3RL to the simulated episodes to estimate the values in the root. So for instance, you could instantiate simulation-based search by using Monte-Carlo prediction to estimate the state value of a root node by using just two components. You have some learned model and some simulation policy. And then the state value in the root will just be estimated by sampling using the model and the policy k episode returns, and then just averaging this to estimate the state value of the root. Of course, if we're interested in planning for action selections, and we are, just the state value in the root might not be that useful. So often we will want to actually construct action values. But the same principles apply very, very naively just also to plan the local action value functions. In this case, we will need k times the number of actions episodes to ensure we sample each action k times in the root. But apart from that, then we can use the same mechanism to generate complete episodes from the model and the simulation policy, and then just again use averaging to estimate the value of each action in the root as the average of the returns that did execute that action immediately in the root and then followed the simulation policy afterwards. If we construct such a local action value function, then it's trivial to turn this into a mechanism for action selection, because we could, for instance, in each state always pick the action with the highest value according to our local search. In the simulation-based search algorithms that I just described, each simulation is independent of the previous ones. And this means that we might not actually be making the best use of the available compute. So it has some computational advantages because it's fully parallelizable. But at the same time, we are not using what we have learned by rolling the model forward until the end of the episode to guide our behavior in the next simulation. So in this second part, I want to discuss a different approach where we build the tree incrementally so that we can leverage knowledge from previous simulation in order to focus our computational resources where they matter most. So the algorithm is called the Monte-Carlo tree search and was, for instance, at the heart of the famous AlphaZero system and AlphaGo, and more recently the mu0 system that showed that they could literally learn at the level of world champions games like Go, chess, shogi, and even video games. And the algorithm is fairly simple because it's just based on repeating the following 4 steps until you have exhausted the computational time or computational resources that you have allocated to the action selection. And on each step, for each simulated episode, what you do is just you start from the root and you use your current estimates of the Q values based on the previous simulations to walk all the way from the root to a leaf node in the tree. Then what you do is you add the nodes to the tree by expanding the action with the highest value in the leaf node. You then use a rollout until episode termination using a fixed stimulation policy to get a complete evaluation of that path in the tree. And then you walk backwards all the way to the root, updating all the Q values of all the ancestor nodes in the tree. And once you have exhausted available time and resources, you just, as in the previous algorithm, just select the action in the root that has the highest value. The important feature of this approach is that effectively we have 2 policies. We are not always expanding nodes and building the tree using a fixed stimulation policy. Instead, we have a tree policy that we use to navigate from the root to a leaf that is based on all the previous simulations. So it's guided by all that we have learned in the previous simulations in this state. And then we have a rollout policy that is this indeed fixed that we use to get the Monte Carlo estimate of the return from the leaf onwards. And often the advantage is that the rollout policy might be very cheap. So for instance, we could just have a random policy. Even that can be surprisingly effective. But because we are iterating on the tree policy that we use to navigate all the way to the leaf, the system actually allocates resources and computes quite effectively and can result in very good value estimates. Of course, at this stage, it might still feel a bit fuzzy. So as usual, let's try walk through a concrete example so we can understand how this algorithm works in practice. And let's consider a situation where we have some state that we are interested to select an action in. And we have always 2 actions in every state. So at the beginning, the tree is empty. So what we do is we just, the initial state is a leaf itself, and we just use a default policy to roll out until an episode termination. So this will, for instance, give us, if we roll out the policy and the model until the model tells us that the episode has terminated, maybe we get a return of 1. Then we update our value of the root node to be 1, because it's the average of the existing simulations. Then we expand 1 node. So for instance, we have no additional knowledge. Let's say we randomly choose to pick the right action. Then what we do is, again, we have reached the leaf. We use the default rollout policy to get an entire episode evaluation. This time, we observe that we get an episode return of 0. But now we go back and we update not just the node we had just expanded, but all the ancestors, which now include the root node. So the evaluation of the node we just expanded will be 0, but the evaluation of the value of the root will have been updated to 1/2. Since the value in the root is higher than the value of the actions that we have selected, then let's try to expand a different action. And again, after reaching this leaf node, we use the rollout policy to get an evaluation. This time we observe a return of 1. So we update the value of this node we just expanded, but also the root. So the root now has the value of 2/3, and each of the actions in the root have an estimate of 1 and 0 respectively. Since the value on the left side is higher, let's now, again, we navigate until the leaf, we expand 1 node, we do an evaluation. This time we observe a 0, we back up all the updates. So the newly added node has a value of 0, his parent has now a value of 1/2, and the root node now have also a value of 1/2, because 2 out of 4 the episodes that started in the root had the reward of 1 and the other 2 had no reward at all. Again, we navigate until the leaf, we pick the action with the highest value, and we expand that node, we roll out until the end, we get an evaluation of 1. Now again, we have to update all the values in the parent nodes to include the latest information that we have generated with this rollout. Again, you start in the node, you follow the Q values to reach the leaf by always selecting the highest value, and then expand again. And if you iterate this process, you basically get a very highly selective best first search, where states are evaluated dynamically, and we are using sampling to break the curse of dimensionality, and while still being computationally efficient, because the algorithm is anytime. So you can basically iterate until you have computational resources, until you have time to think, and then at any point you get a best estimate of what the agent can assume the values in the root to be, given the policy and the model that it had available. An important thing to realize, though, is that Monte-Carlo tree search, but actually basically all the simulation-based and even forward search, are essentially table lookup approaches, but based not on instantiating the table of all possible states, but instantiating a partial table that only includes the most likely state or that are directly reachable from the current state. So we discussed quite extensively that for model-free RL, table lookup is maybe a bit naive. So you cannot possibly store values for all states. And because you don't get any generalization, you will likely not have trained a value or a policy for any new state that you encounter when interacting with the environment. But for simulation-based search, the table lookup is actually less naive, because you only need to store values for the easily reachable states that are likely under the policy and under your Q value estimate. So even if you don't have extensive generalization, this can actually be a system that works quite well in practice. At the same time, there are limits. So it is still a partial instantiation of a table, and that could grow to be very large. So for very big large search spaces, it will still be useful to combine these ideas from MCTS with, for instance, value function approximation. This is, for instance, what actually the AlphaGo system did. It actually used value functions and policies to guide the search, and in its later iterations, even to replace the rollouts to get Monte Carlo evaluation by rolling a leaf all the way to the end, replacing that with just a learned value function to basically make the process more efficient.